So this lesson is on exponential relations, and it relates to exponent laws because what we're doing here is we're basically taking a exponent, or rather a power, and we're turning that power into a function or a relation. So rather than evaluating a power as where we know both of the values, the value of the base and the value of the exponent. In this case, we're going to create a function where we have a power and the exponent is our independent variable, the variable that changes. So let's look at what this would mean. And there's really kind of two sort of forms that we would see. When we have a relation of the form y equals b to the power of x, in this case, b always has to be greater than 0. We can't have a negative number for this because it wouldn't graph when we have a negative exponent. And b cannot be equal to 1 because in that case, then it's no longer an exponential relation anymore. So when we have an exponential relation of the form y equals b to the power of x, the y-intercept is always 1, and it does not intercept the x-axis. It'll get close to the x-axis, but it will not intercept it. It'll have what we call a horizontal asymptote at the x-axis. And when b is greater than 1, we have what's called a growth relationship, and when b is between 0 and 1, we have what's called a decay relationship. And we'll look at what those two mean shortly as well. So the graph for a relation when b is greater than 1 looks like this. This is our exponential growth relation graph. And you can see that it has an asymptote at the x-axis. It does not cross that x-axis, but it grows exponentially. It grows much faster as our x value increases. And the opposite graph, when we have a value for b that's between 0 and 1, is what we have called a decay relationship. And you can see this is the opposite because in this case, as our x decreases, we have exponential growth, but as our x increases, we have exponential decay. Now, let's make this a little bit more complicated, and we'll write this in the form y equals ab to the power of x. So if we add that a in front, our y-intercept would now be at 0a, and the critical points for graphing would be at 1ab and negative 1a over b. So you can graph those 3 points, and you can sketch a pretty good exponential curve for any exponential relation of that form y equals ab to the power of x. The next part of this lecture talks about how we see exponential relations in many different applications. So in nature, they occur with the radioactivity of a substance. It will decay over time. We can see the concentration of a material will increase or decrease exponentially. Population growth does the same. When we talk about financial math, which we'll do in our next few lessons, they are all graphed based on exponential relations as well. So this example question here, it says y equals 3 times 1/2 to the power of x. So our a is 3, our b is 1/2. We're asked to make a table of values and to sketch this. So to start with, we make our table of values. We should choose values between -2 and 2, just so that they're close to the 0. What we'll notice is when we put in -2, we get a relatively big number of 12. If I put in -1, I get 6, 0 gets me 3, 1 gets me 1.5, and 2 gets me 3 over 4, or 0.75. As I graph that, you'll see that it's an exponential decay relationship. I cross the x-axis at 0, 3. At 1, I'm at 1/2, or sorry, 1 and 1/2 for y, and at -1, I'm at 6. So using those 3 points, I can sketch this curve. Let's look at another question that doesn't involve graphing, but instead involves an exponential relation. And this one is an exponential relation for population growth. So we have a city, the population is 245,000, and it increases by 35% each year. What we would do here, first in this question, we are asked for part A, what's the initial value of this function and what does it represent? So the initial value of the function is what we see there for our A. It's 245,000. What it represents is the population in the year 2020, because the value of n represents the years after 2020. So we put 0 in for n, we should get this value. Well, we will get this value. To find out what the population is going to be in 2035, we have to figure out what our n is going to be first. So if we do 2035 minus 2020, we end up with 15. So we're looking at a 15-year increase. So I multiply that initial value by this growth factor to the power of 15. And I end up with a number of 410,460. And I would round that, and in this case I'll round it down. That's how many people we have in terms of our population in the year 2035. Let's look at some sample problems here. So the first one involves sketching. So I will make a table of values and I will sketch one of these functions. Let's do D. That one looks like the most complicated, so I'll do 1D. So let's see here. For 1D, I have y equals 0.125 times 2 to the power of x. So in this case, for my x, y values, let's choose something a bit greater here. So let's go with, we'll do -4, -3, -2, -1. We'll do 0, and then we'll do 1. So at 0, I will have 1 for this term, and I'll have 0.125 over here. Oh, you know what? Actually, this is not a good table of values. Sorry, I should redo that. I meant to do this the other way. So basically, what I'm trying to do in terms of choosing my numbers is to have values that will try to reduce our fractions as much as possible. So let me scratch that out. We'll start again with, we'll just do -1, 0, 1, 2, 3, 4. So at 0, I'm at 0.125. At -1, I have 1 over 2 here, so this becomes, well, this is actually 1 over 16 now. When this is a 1, I have 2 times that. I end up with 1 over 4, or 0.25. And then I'm just multiplying by 2 each time, so 1/2, 1, and 2. So to graph this, what I end up with is, let's make our, oops, should have a ruler, but I don't have one with me right now. 1, 2, 3, 4. And I'm going to make this, if this is 1, 2, 3, 4, 5. So in this case, it's going to be pretty small. -1, I have to get 1/16. So that would be about here. And at 0, I'm going to be at 1/8, which would be about here. At 1, I'll be at 1/4. At 2, I'll be at 1/2. At 3, I'll be at 1. At 4, I will be at 2. And let's just increase this here by 5. We'll be at 4. At 6, I will be at 8. 6, 7, 8, which puts me up here. So my function ends up looking like this. So that's my sketch for 1D. For 2, in this case here, so I'm asked to determine the concentration of this drug after 8 hours. And I have the formula for the concentration of the drug. I just have to substitute 8 in for T. So I'll show you how to put this in your calculator. 50 times 1 over 2, close the bracket, to the power of bracket 8 divided by 4. That gives me 12.5. So my answer for 12A is 12.5. Now the next part I'll do on the paper here. So it says, what's the concentration of the drug? After how many hours will we have the concentration of 25? So in this case, I start with C equals 50, 1/2 T over 4. 25 equals 50, 1/2 T over 4. 25 over 50 is the same as 1 over 2. So in order to get this 1/2 to equal this 1/2, I need to make this term here equal 1. So T over 4 has to equal 1, which means T has to equal 4 hours. Now for question 3, I can just do it on the calculator. It says that I have a population of 59,000. I'm increasing by 13%. The first part says, what is the initial population and what does it represent? So the initial population would be 59,000, and that represents the population in the year 2011. What's the projected population? So I have to raise this growth factor to the exponent of, sorry, you guys aren't seeing that there, eh? Raise that to the exponent of 2028 minus 2011. 17. So I end up with this value here, and I'll round that to 73,487. Okay, lastly, what I'd like to do now is I want to show you how to do the what the quiz will look like. So in this case, your quiz is going to have 4 questions. You'll have to sketch something like this. Then you'll have to answer some exponential relation questions, just like these here. And I will, I'll work through the last one with you. It says the population of a bacterial culture grows at a rate of P equals 100 times 2 to the power of n, where P is the population and n is the time in hours. How long will it take until the population is 8 times larger? So in this case here, what you need to do, I won't go give you the full answer to this one, but what you'll need to do for this question is, let me just move this around so that we can see. For this question, what we need to figure out, if our population is determined by this, and we have to find out when it's 8 times larger, well, our initial population is 100. 8 times larger would be 800. So I basically need to solve this equation. And I need to solve that for n. So I'll leave that to you guys to work on. And if you have any questions, just let me know when you're taking the quiz.